Good afternoon, my name is Dr. David Nuttall. I want to talk about Newton's three laws of motion. First of all, what are forces? Forces may push or pull one body on another. Forces always occur in pairs, which is important when we discuss Newton's third law. And there are four types of force: gravitational, electrostatic, magnetic and nuclear. Also there are two types of force other than that: contact force and non-contact forces. Contact forces exist between bodies which are in intimate contact, which they are essentially electrostatic forces acting over very small distances as a result of electron repulsion. All forces involved in friction, for example air resistance, viscous drag forces and normal reactions, are contact forces. And of course there are non-contact forces which, as the name implies, act at a distance. Gravitational, electrostatic and magnetic forces can all be regarded as non-contact forces. Why are these important? It's important to distinguish between these forces because when we draw free body force diagrams or consider Newton's third law problems, we need to know about contact and non-contact forces. So, first law of motion: a body stays at rest or in uniform velocity unless acted upon by resultant force. So a simple example: you're all used to riding in cars, and if the driver suddenly puts the brakes on, we tend to move forward, or accelerate, we move back like that. And to illustrate inertia, we can put a coin on a postcard shown in the slide, and if we suddenly pull the postcard away, of course the coin falls into the tumbler. Books resting on table, so there's a reaction force between the book and the table pushing upwards, shown in the slide, and the weight or the force of the book on the table pushes downwards, and at equilibrium of course they're at rest. Same thing applies to the legs of the table acting on the floor, as shown in the diagram. A string under tension, so if we have a plumb bob of weight mg attracted by the earth with force mg, there's a tension upwards to maintain the weight in equilibrium, and of course there's a tension on the ceiling shown as the upper T pulling downwards. And one more example: although it's moving upwards on an incline, an object moving with constant velocity has no resultant force acting on it, so even an aeroplane climbing like that at a steady angle, there's no resultant force acting on it. Newton's second law of motion, often referred to as F equals ma, states that the rate of change in momentum of a body is proportional to the resultant force that acts on it and takes place in that direction. So mathematically, shown in this slide, the momentum of a body is the product mv, where m is the mass and v is velocity. So if the force F which changes momentum is given by F is proportional to d by dt of mv, so for a constant mass F is proportional to m dv by dt, which is proportional to ma, where a is acceleration. So Newton decided to let k is equal to 1, so since F equals kma, then we have the usual form F equals ma. So here are three examples of Newton 2. In the first example, the block is stationary, there's 20 newtons pulling it each way, which means that there's no overall force, so it's just static. In the second example, acceleration occurs. Why? Because there's 2000 newtons of friction, 6000 newtons of engine thrust, so obviously there's a resultant force of 4000 newtons pulling it to the right. And in the third example, C, the skier is moving at constant velocity, and although there's a 400 newtons of friction, he's thrust himself forward 400 newtons, so there's no overall force. So that is another example of Newton's second law. And the second example is a powerboat pulling a skier, and it says here in the slide if the resistive force is acting on the skier and the boat at 80 and 20 newtons, we want the tension in the rope and the driving force of the speedboat engine. So the solutions to these, if we draw a free body force diagram for the skier and the boat, so considering them separately, that's the way to do it. If T is the tension in the tow rope, m is the mass of the skier and a acceleration, then T minus 80 equals MA, which is 60 times 3, which is 180, and this gives tension in the rope as 260 newtons. Second part, if F the driving force, then because there is 260 newtons tension in the tow rope and 200 newtons of friction, they both act in the same direction, so F minus 200 minus 260 is equal to MA, where M is the mass of the power boat, which is 900 kilograms, times 3, acceleration, is 2700, which gives F is equal to 3160 newtons. That's the solution to that. And the third law of motion is when two bodies interact, the forces they exert on each other are equal and opposite. This is sometimes called action and reaction are equal and opposite. So for example, rockets and jets. The backward force of the rocket on exhaust gases is equal to the forward force of the exhaust gases on the rocket. That is one example in Newton 3. These are examples which are not third law pairs, actually. So in the first case, there's only one body, in case A. So there's 15 newtons each way, they're equal and opposite, but they only act on one body, so that is not Newton 3, they must have two bodies. Number B, there's 35 newtons, but both act in the same direction, so that cannot be a third law pair of forces. Slide C, although they are both in opposite directions and on separate bodies, they're not acting in the same line, so that is not a Newton's third law pair. And finally, slide D, there is 47 newtons of gravitational force and 47 newtons of electrostatic force, different types of force, so that is not a Newton's third law pair of forces. So if you want to investigate this further, I recommend you visit www.alevel-physics.co.uk. Thank you very much for listening, and bye, and good luck with your physics.